The surface of the sun burns at 10,000 degrees Fahrenheit. 4 million miles from that furnace, NASA's Parker Solar Probe takes 2,500 degrees on one side of its shield, while the instruments behind it sit at room temperature. That's not magic. It is a carbon sandwich that took a decade to perfect, and no conventional material could survive what makes this problem so extreme. The physics of space itself dictates the scale of this challenge. Under the inverse square law, the intensity of solar radiation does not rise steadily. It spikes exponentially as distance decreases. At its closest approach of roughly 4 million miles, the Parker Solar Probe faces an onslaught of solar energy 500 times more intense than what is felt in Earth orbit. This environment demands a defense against thermal flux rather than raw temperature alone. Because space is a vacuum, there are almost no molecules to conduct heat directly, but the sheer concentration of incoming radiant energy is devastating. In this regime, conventional aerospace materials fail. Structural steel softens and melts, titanium loses its strength rapidly, and standard industrial ceramics crack under the sudden thermal shock. To survive this unceasing solar bombardment, the engineering team at the Johns Hopkins Applied Physics Laboratory had to look beyond standard metallurgy and completely redesign how a spacecraft interacts with a star. The engineers at the Johns Hopkins Applied Physics Laboratory solved this by developing the thermal protection system, an 8-foot diameter circular shield measuring just 4.5 inches thick. Instead of a heavy solid barrier, they engineered a lightweight, multi-layered carbon sandwich weighing only 160 pounds. The outer structural skins consist of carbon-carbon composite face sheets. Carbon-carbon is an extraordinary material for this application because, unlike metals that weaken when heated, carbon actually gains strength at extreme temperatures, maintaining its structural integrity far beyond the melting points of most superalloys. Between these face sheets lies the core of the shield's insulating power, a carbon foam layer. This foam is created through a specialized pyrolysis process that leaves an open cell lattice of carbon struts. Because the resulting structure is 97% air, there is almost no solid matter available to conduct heat from the front of the shield to the back. This geometry ensures the delicate scientific instruments remain safely nestled in the cool shadow, or umbra, cast by the shield. To completely isolate this heat from the rest of the spacecraft, the team had to rethink how the shield attaches to the frame. A wide mounting surface would act as a thermal bridge, conducting lethal amounts of heat directly into the electronics. To prevent this, Johns Hopkins Applied Physics Laboratory secured the entire 8-foot structure using exactly 6 titanium attachment points. These narrow, high-strength brackets minimize the physical contact area, choking off conductive heat paths and keeping the delicate payload safe. The carbon-carbon structure alone is not enough to survive the approach. Left bare, the black face sheet would absorb the sun's intense radiant energy, quickly overheating the spacecraft. To prevent this, Johns Hopkins Applied Physics Laboratory coated the sunward side of the shield with a white aluminum oxide ceramic. This reflective layer bounces over 99% of visible solar radiation back into space. However, spraying the ceramic directly onto raw carbon creates a volatile chemical hazard. At temperatures above 2,000 degrees Fahrenheit, carbon and aluminum oxide react, causing a chemical breakdown that darkens the surface and destroys its reflectivity. To isolate these materials, engineers deposited a thin tungsten separator layer, thinner than a human hair, directly between the carbon face sheet and the ceramic coating. This metallic barrier completely blocks the high-temperature reaction, yet the ceramic coating still faces the threat of grain growth. Under extreme heat, the ceramic's microscopic grains naturally coarsen and expand, turning the white surface dull and gray. To preserve its whiteness, engineers introduced nanoscale silicon dopants. These nanoparticles settle at the grain boundaries, pinning the microstructure in place and keeping the shield highly reflective. This multi-layered optical system delivers an extraordinary thermal performance. At the spacecraft's closest approach, roughly 4 million miles from the sun, the front face of the shield reaches a blistering 2,500 degrees Fahrenheit. But just 4.5 inches behind it, the rear face registers only 600 degrees, while the scientific instruments operate at a comfortable 85 degrees. It is a temperature drop of nearly 2,400 degrees, achieved across a barrier thinner than a standard household brick. To collect data, the probe cannot hide entirely behind its shield. The solar probe cup, designed to measure ion and electron fluxes, must extend past the protective shadow, directly into the unmitigated flux of the sun. To survive this exposure, the Johns Hopkins Applied Physics Laboratory turned to extreme metallurgy. The cup's housing is machined from a titanium zirconium molybdenum alloy, which boasts a melting point of 4,260 degrees Fahrenheit. Inside, the cup uses electrostatic grids to filter charged particles. These grids are made of tungsten, a refractory metal that melts only at a staggering 6,192 degrees Fahrenheit. But manufacturing these tungsten grids proved to be its own engineering bottleneck. Traditional laser cutting trials failed, leaving microscopic cracks along the edges that threatened to fail under extreme thermal cycling. The engineering team solved this by using photolithography and a specialized acid etching process. Immersing the patterned tungsten in a wet chemical acid bath opened the sub-millimeter apertures cleanly, creating flawless microscopic edges that resist electrical arcing. Managing power generation required another dual-action solution. The spacecraft's solar arrays must generate electricity, but exposing them fully to the near-solar environment would instantly destroy them. The team mounted the arrays on motorized actuators, allowing them to retract behind the shield's shadow, exposing only a tiny sliver of their surface during close approach. To keep the cells from overheating, water pumps circulate deionized water through microchannels behind the panels at a rate of 1 gallon per minute, carrying excess heat to radiators that dump it into the cold of space. By solving these localized thermal crises, the team ensured the entire spacecraft functioned as a single, surviving organism. On April 28, 2021, the Johns Hopkins Applied Physics Laboratory witnessed decades of engineering transform into pure scientific discovery. The Parker Solar Probe crossed the Alphen critical surface, officially crossing into the solar corona for the first time in human history. Operating roughly 4 million miles from the sun's surface, the spacecraft's shield endured a blistering 2,500 degrees Fahrenheit on its front face, while keeping the scientific instruments behind it at a functional 85 degrees. From this extreme vantage point, the probe gathered direct measurements of solar wind acceleration and magnetic reversals, providing the first physical clues to the coronal heating paradox, why the sun's outer atmosphere is hundreds of times hotter than its actual surface. As the mission continues with even closer passes, this lightweight carbon shield remains the single barrier between human ingenuity and the destructive power of a star. Subscribe to follow more stories of extreme engineering. The materials engineered for the Parker Solar Probe protect more than a single spacecraft. They expand the boundaries of aerospace engineering. Similar carbon-carbon composites already absorb the intense friction of commercial aircraft brakes and shield atmospheric re-entry vehicles. Now the thermal protection design validated by the Johns Hopkins Applied Physics Laboratory directly informs next-generation heat shields for crewed Mars missions, where spacecraft must survive extreme atmospheric friction. By proving that lightweight carbon structures can endure solar temperatures, these materials establish a new design space. They enable future architectures to explore the most punishing environments in our solar system. By conquering the sun's brutal frontier, Johns Hopkins APL didn't just build a shield, they redefined the limits of human exploration. The materials forged for this mission will pave the way for our journey deeper into the cosmos. Subscribe for more deep dives into extreme engineering.